So in this lesson, we'll cover operations for the matrices. It's like all the algebra of matrices. We will be covering them in this this lesson, and that will be the content for homework 4 of the chapter 11 or section 11.4. So we went over the disposition of the numbers in a matrix already. So that's the same thing that we saw for in lesson 2, right? So this time it's more doing operations over a matrix. So this is an example of the disposition of the matrix, and this is the description of all the elements that will be in it. And say, for example, so you have a survey of 900 people, and we have the following information to put in a table, right? So there is 200 males that are 200 males thought federal defense spending was too high. We got 150 male thought that federal defense spending is too low. 45 male had no opinion. So we have 3 characteristics: too high, too low, no opinion. And then we have 3 categories. Actually 2 categories: male and female. Well, when you come here, so you see the too high, too low, no opinion, and male, female in the rows. So the rows will be everything about male, and the first row will be everything about male, the second row of everything about female, and then the rows are the characteristics. And it gives you the table, and you have a matrix with 2 lines, 2 rows. That's row 1, row 2, and 3 columns, which are the characteristics: the too high, first row, and first column, sorry, and too low is the second column, and the third column is no opinion. So that's a matrix, right? But obviously you see it's a table, and where every number has a specific significance, specific meaning. Okay. Now let's see how we can operate over the matrix, how we can do the algebra of matrix. First thing we do is equality of matrices. Well, if you have 2 matrices that are equal to each other, that means they have the same elements in them, including the same elements at the same position. So that means all the if A equals B, 2 matrices, that means all the Aij are the same as the Bij. Here are some examples. Oh, well, we don't have. Let me give you one quick example. So say I have 1, 2, 4, 0, -2, 3, and 7, 5, -3. That's a 3 by 3 matrix, right? That's a 3 by 3 matrix, means it has 3 rows and then 3 columns. Now say that this equals to this matrix A, B, C, X, Y, Z, T, 3, T, U, and V. Well, these two are equal. It's mean the numbers in the same position are the same. So that automatically means that A equals 1, B equals 2, C equals 4, and so on. X equals 0, B equals -2, or B, that's not B, that's Y. Y equals -2, Z equals 3, T equals 7, U equals 5, and V U equals 5, and V equals -3. The numbers at the same position in the matrices, they are equal. So then you cannot have two matrices with different dimension. Dimension means the number of line, number of columns that are not same. So if I have a 2 by 2 to A, B, and 4, that cannot be equal to a matrix that has more column than this one, or more rows than this one. They have to have two matrices will be equal to each other when they have the same number of rows, the same number of columns, also the table or the same exact number arranged in the same exact or similar way. So that's what you need to know about equality of matrices. The next thing is operation, addition, and subtraction. So you add the numbers in the same location. So say you're adding these two, they are the same dimension. And also if you're adding to let me say this. So if you're adding two matrices, they must have the same dimensions. Let's try this one. So A plus B equals, that's my table, this one plus this one. So that is 2 plus -3. This one plus this one, that's 4 plus 4. This one plus this one, that is 8 plus 0. And this one plus this one, so that is -3 plus 1. Now let's go for the second row. Weaker, 0 plus 6, 1 plus 8, 2 plus 2, and 3 plus 0. That equals, that's -1, 8, 8, 6, 1, 9, 8, 8, and then I'm missing one here. That's negative 2, 9, 4, and 3. That is the sum of A and B. Let's do the subtraction. Subtraction, we're gonna go as quick as we were going. So basically it'll be the same thing here, right? The same that we have here with a minus sign instead of plus sign. For the second element, right? That's a minus, 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 and minus. And your answer will be, so let's fabricate the answer 2. Obviously, we're not using the numbers, we're just using the brackets. So that's 5. That's 5. So that is 5, 0, 8, negative 4, negative 6, negative 7, 0, and then 3. So that is the answer for the operation subtraction and addition of these two matrices. Now, as we know that we can add and subtract matrices, and we know that some of the properties in real numbers, they apply to some of the properties in the set of matrices, but it's not all of them. So one of the things that works in the set of matrices is the commutativity of addition. So commutative property of addition is also maintained in the sum of matrices. So if I have A plus B and A plus B, it's the same as B plus A. It's the same. However, multiplication would not work. Subtraction, you know, it's not work. It doesn't work. But also, if I have the product of a constant with a matrix, it works. Also, if you have a sum of matrices multiplied by a constant number, you can distribute it. Okay. And then, by the way, multiplication of a matrix by a constant is that you multiply this matrix by each constant inside of the matrix. So we also have what we call a row vector and a column vector. So a row vector is a vector that has one column, but it has more than two column. It has one row and then n columns. That's a row vector. One row and then more than one row, more than one columns. And it's similar situation for the column vector. The column vector is a matrix that has just one column, and then you see multiple rows. So in this case, since it has one column, it's called a column matrix. or vector. And you can multiply the two because we will see multiplication, but basically when you multiply a row vector by a column vector, you just multiply the elements by each other, the numbers, the elements with the same numbers together. So that explains why the product of the row column and the column, the row vector and the column vector is equal to R1C1, R2C2, and so on. So that because you multiply the entry with the same numbers together. So we need to note that a row vector and a column vector can be multiplied if and only if they both contain the same number of entry. So you see in this case, we had n entries for the row vector and n entries for the column vector. So because they have the same number of entries, then you can multiply them. Otherwise, the multiplication is impossible. The multiplication is impossible if the product is impossible if the row vector and the column vector, they don't have the same number of entry. So let's look at this example. In this example, we have the row vector that is 3, -5, 3, -5, and 2. And then the number of entry is 3. Here we have 3, 4, and -5. The number of entry is 3. The product of the row vector times the column vector is possible. Then we can go ahead and perform this as we are asked to do. So how we do it? It's row vector times column vector equals the row vector that is 3, -5, 3, -5, 3, -5, and 2 times the column vector that is 3, 4, -5. So that equals the numbers on the same entry number. That's 9. Let me put it 3 times 3 plus these 2, -5 times 4 plus these 2 times -5. So combined, that's 9 minus 20 minus 10. So that is -21. Right. So next example. In this example, what are we being asked to do? They said using matrices to compute revenue. A clothing store sells men's shirt for $40. Silk ties for $20 and wool suits for $400. Last month, the store sold 100 shirts, 200 ties, and 50 suits. What was the total revenue from this sale? Well, basically, we are asked to do something similar to what we had earlier. So if we call the row column the row vector as the price for the product. So that equals the prices of the product. Then you would have, this is, since it's the row vector, we're going to put all the prices in it. So that's $40. That is the shirt. Men's shirt. Also, we have the ties. Also, we have the suits. Okay, 40, 20, and 400, right? And then the next one will be the number of products sold in each category. So that's the column number of sale for each category. Right? So that is 100 for the shirt, 200 for the ties, and then 50 suits. Now, if we multiply these two columns and row vectors, we would automatically get the revenue for this sale, these sales. So that is revenue that equals RC. So that equals the row vector that's the row vector times the column vector. This one first. So that's going to be the result for the revenue. That is 40 times 100, that's 4,000, plus 20 times 20,000, that is 20 times 2,000, that's 4,000, plus 400 times 50. So the revenue for this entire sale is $28,000. So that's $28,000. Well, you would say that this is the revenue for shirts, revenue for the ties, and that's the revenue from the suits that give you the total of 28,000 in revenue. Now let's talk about multiplication of matrices. Multiplication. Now we need to say that the multiplication of matrices, that's called that is also the product of AB. So M by N, if you have a matrix that has M row and N column, you should make sure that the dimension of the matrices are like this. Though the second one is like this. Number of column of the first one is the number of row. Number of column of the first one is the number of row of the second one. And then it's okay. You don't have to compare the two other numbers, but number of column of the first one must be the number of row for your multiplication to be defined. That's what I say here. They must be the same. Now, first, when you're multiplying two matrices, the first thing you would check, look at the number of column of the first one, and look at the number of row of the second one. If the two numbers don't match, you just say the multiplication is not defined. Now let's multiply these two. How many columns? 1, 2, 3. How many rows? 1. How many columns? 2. Sorry. Number of column? Yes. And how many rows here? 1, 2, 3. So the number of columns is the same as the number of rows, then this multiplication is possible. And then the matrix that you're going to receive at the end would take the same number of row, the same number of columns of row that you have in the second. The number of row in the first matrix is the number of row of the result. So your result will take the same number of row that is 2 here. And then the number of matrix the number of column, the result will be the same number of column of the second. So what am I trying to say you're multiplying A and B, right? For your multiplication AB to exist, you need to have the same number of column of the first matrix, or the A is equal column, number of column, is equal number of column of the first matrix is equal to number of rows of the second matrix. And then the product AB will have the same number of row or column of the first and the same number of row of the same number of row of the first and the number of column of the second. So it will be, the result will be a matrix of dimension M by N. So our number of column of the first should match the number of row of the second, and the result will be a matrix with the same number of row as the first and the same number of column as the second. So we know that this product is possible because this matrix, these two matrices, they have the same number of column. The first one has the same number of column 3 as the number of row 3 of the second. Now we expect the product AB to be possible, and we expect a result of a matrix that has 2 rows, which is the number of rows of the first matrix, and then the number of column is 1, 2, 3, 4, and 4 columns. So 4 columns. Now, how do we get them? We're going to multiply by rows, the vector rows and column. Rows and column. Now, we can see how we will multiply these two vectors. So that's the first one, that's row 1 and column 1, right? And then it'll create row 1 and column 1 in the new matrix. So that means I'm going to multiply 2 times 2 is 4. 4 times 4 is 16, and -1 times -3 is +3. So that's 16 plus 7, 23. Okay, and then we're gonna continue that, right? So we would do the same, but let me multiply all the first rows with all the columns. So basically, they will create my first row of my new matrix, right? So now let me go with the first row and first column and first row and second column, right? So that's 2 times 5, 10, 4 times 4, 4 times 8, 32, -1 times +1, that's -1. So that gives me 41. Let me work with the first row of the first matrix now and the third column of the second matrix. So that's the first row and the second, and the third. The first row of first matrix and third column of the second matrix. So that's 4 times 2, that's 2. 4 times 0, 0. And -1 times -2 plus 2. So that's going to be 4. And then let's now finish with the first row of the first matrix with the first row and fourth column. First row and fourth column. So that is 2 times 4, 8. 4 times 6, 24. And -1 times -1, +1. So that's the total of 33. Now that I finish with the first row in the first matrix, I can go ahead now, start my second row that will create the second row of my new product matrix. All right, so that's the row that I'm going to be working with, right? So let me start with row 2 and column 1. row 2 in column 1, that's this. So it will create the number that will go in this location. All right, so then that's 5 times 2, 10, 8 times 4, 32, 0 times -3, 0. So that's 42. Same row, but the second column now that would go here, that's second row and second column. Second row and second column. So that's 5 times 5, 25. 8 times 8, 64. 0 times 1, 0. So that number is 89. Next, we will multiply second row and third column. Second row, third column. 5 times 1, that's 5. 8 times 0, that is 0. 0 times 1 is 0. So we have 5 right here. And then finally, to complete the multiplication, we will multiply second row of the first matrix with the fourth row of the second matrix. So that's 5 times 4, 20. 8 times 6, that's 48. And then 0 times -1, that's 0. So that totals to 68. And that is the product of A and B based on these two given matrices. So that's the explanation of what I was saying. So that should give you so that's the explanation. So I just did it in once, but I hope that you understand the steps instead of me doing too much and that gets you confusing, because I know multiplication of matrices is kind of confusing. So you need to make sure you practice on that. Now, next, we will see whether we can multiply these two, and then go from there. But we are trying to multiply. We are trying to see if we can multiply A, find AB, and B, find BA. See if we can do that. If it's possible, if both of them are possible. So what is AB? Is AB possible? So we're going to try to see if the number of column here is the same number of row here. Number of columns is 1, 2, so number of column is 2 and number of row is 2 as well. So we can perform AB. So let's go ahead and AB equals, that is the A, 2, 1, 3, 1, -1 and 0. And then 1, 2, 3, 0, 1, and 2. Now let's perform the product. We're going to consider the first row. And then we know that we will get the number of the result product will have the number of rows of the first matrix, which is 1, 1, 2, and the number of row and the number of columns of the second matrix, which is 1 and 2. So we're going to have a 2 by 2 matrix. A 2 by 2 matrix. So how we get that? The first here, you would be column 1 times row 1, right? So let's do column 1 times row 1. So that is 2 times 2. 2 times 1 is 2. 1 times 2 is also 2. And then 3 times 3 is 9. So that's 13. Now let's do column 1 times column 2. Well, column 1 times column 2 will go here because this is the location you would say that's column 1 and that's row 2, column 1. So row 1, column 1, sorry, row 1, column 2 is right here. Row 1 and column 2, that's it. That's where it is. So we're gonna put this product here. 2 times 0, 0, plus 1 times 1 is 1, plus 3 times 2 is 6, so that's 7. Now we're done with the first row of the first matrix. Let's work with the second row of this matrix. Row 2, column 1. Row 2, column 1 is here. That's here, right? So 1 times 1 is 1. Negative 1 times 2 is negative 2. 0 times 3 is 0. So that's negative 1. And then finally, we're going to do row 2 and column 1. I mean, column 2. Row 2, column 2 is here. So we would put the result right here. So that's 1 times 0, 0. Negative 1 times negative 1. Negative 1 times positive 1 is negative 1. 0 times 2 is 0. So that's negative 1. So the product is 13. Let me try if we get the row 1, column 2 right. Row 1, column 2, so that's this. We got 2 times 0, 2. Oh, no, 2 times 0, 0. I think that's what we got wrong here. 1 times 2 is 2. 1 times 1 is 1. And then 3 times 1 times 1 is 1. And 3 times 2 is 6. Yeah, so that's 7. In my notes, I see that I had something different. Let me see. Okay, so that's right, 7. So that's it for the product. Like I said, multiplication of matrices is kind of a lot of operations. Then you need to have your head in place and practice. So let's see the B times A. So B, we're gonna multiply matrix B times the matrix A. That equals matrix B now becomes the first matrix. And then A becomes the second. So we would need to say that the number of column, which is 2, C equals 2, it should be the number of row over here that is also 2. And the expectation is that the result, so when we check that, it tells us that the product is possible. Now, next, we're going to try to see what type of matrix we're gonna get. So it will be the number of rows of this will be the number of column of this. And when we look at that, we see that we're going to have a 3 by 3 matrix, because the number of columns, the number of rows here is 3, and the number of columns here is also 3. So 3 by 3 matrix. Now let's go with the first row times the first column. So that's going to be 1 times 2, 0. So that's 2 for the first place. Now let's do it for the second column. So that's plus 1, because we got plus 1 times plus 1, 1. 0 times negative 1, 0. So that's 1. And then let's do for the third column. So that's 3, because you have 1 times 3, 3, 0 times 0, 0. Now let's work with the second column, and then we will distribute it over to all of them. Second column, and then we start with row 1. That's 2 times 2 plus 1 times 1 equals 5. And then now let's do it with the second column. Two times 1, 2. 1 times negative 1 minus 1, so that's 1. And then let's do the third column. That is 2 times 3, 6. 6 plus 0, 6. Okay, and then now let's do for the last row and the columns. The last row, we're going to go column 1, then column 2, then column 3. Column 1 is 3 times 2 plus 2 times 1, 6 plus 2 is 8. Now let's work with column 2. That's 3 times 1 minus 2 times 1. So that's 3 minus 2 equals 1. And then lastly, we're going to do 3 times 3, 9, plus 2 times 0 is 0. So that's 9. And that completes the product of B and A given the two matrices that we will multiply. So now let's talk about square matrices. Well, the square matrices are matrices that have the same number of rows and columns. Well, if two matrices have the same dimensions, the product of both sides exists, and it'll give you the same dimension. In this case, we have A equals 2, 1, 0, 4, and that's how you read it. You read it for rows, from left to right, and you read the rows. Row 1 first, row 2, and so on. So 2, 1, 0, 4 times B, negative 3, 1, 1, 2. So now let's go ahead and multiply AB. So we got AB equals the first square matrix 2, 1, and 0, 4 times the second square matrix -3, 1, 1, 2, right? Now let's multiply. First, we're gonna work first row with the first column, then second column. So first row with first column, that's 2 times -3 plus 1 times 1. So that's -6 plus 1. That's -5. And then we're going to work with the second column in the first row. So that is 2 times 1 plus 1 times 2. So that is 4. We said first row. So that's the first row, and we put them in order per columns. Now let's work with the second row. You know, the results will be distributed in the second row of the resulted matrix. All right, then we're gonna do column 1 and then column 2. So 0 times -3 plus 4 times 1 equals 4. And we're gonna go with the second column. 0 times 1 plus 4 times 2, that equals 8. So that concludes the product of AB. Now let's go ahead and work with BA. So we have BA that is equal to, now we put the second matrix first, the B, and then the A comes after it. Now we do the same thing, except we're going to use the B first. So we start with this column, with this row, and distribute it over. We know we're going to have a 2 by 2 matrix. So that's -3 times 2 plus 1 times 1 equals -6 plus 1. -6 plus 1 equals -5. -5. And then now let's go ahead with the second. The second row, -3. Oh, wait, sorry, that's not right. We're working with the first row, right? First row, so that's -3 times 2 plus 1 times 0. So that's -6. That's -6. Now let's work with the second row. The second row is -3 times 1 and then 1 times 4. -3 times 1, -3 times 1, and 1 times 4. So that is supposed to be -3 plus 4, that's 1. That's the first row. Now let's work with the second row. The second row we'll do the same thing. We multiply it by the first row and then the second column. First column and then second. 1 times 2, that's 2. 2 times 0 is 0, so that's 2. I'm done with the first row, second row, and first column. Now let's do second column. 2 times 1 is 1, plus 2 times 4 is 8, so that's 9. So these are the results for the product of A, B, and BC. AB and BA. Now, product of matrices is commutative. It's not commutative. It's not commutative. Product of matrices is not commutative, but it is associative it is associative. And also you can apply the distribution of it on it too. If you have a matrix A times the product of BC, if you want to do the product of AB first and then time the C, it's fine. If you want to do the BC first and then multiply by AC, by AB, by the A, you fine. But you cannot move it to this because it's not commutative. It is not commutative. You can't displace factors in the product, but you can multiply them in the order you choose. Also, you can distribute this, but you can't move position. You can go from AB to BA because basically, as we can see here, we did the AB, we did the product AB, we get a matrix. When we do BA, we get a whole different matrix, which proves, since we have a case where the product of AB is not BA, then you can trust it. So that means you are not allowed to displace factors in a product of matrices. Now let's see. Also, we call identity. The identity matrix is like a 1, but you need to pay attention to the dimension of matrices, because the 1 is having 1 in the diagonal, main diagonal entries only, and zeros otherwise. Now what happens is you're going to have to think about the dimension, because if I'm working with a 2 by 2 matrix, which means I'm working with a matrix where the number of row is the number of column equals 2, then I need to make sure that my identity for this category of matrices is a 2 by 2 matrix. Like the I2 is 1, 0, 0, 1, and the I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. I read in column. I read in rows. And if I have the identity for I4 would be a 4 by 4 matrix. So that's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, no, 0, 1, 0, and then the last row would be 0, 0, 0, 1. So that is the 4 by 4 I. So 1 in the main diagonal and 0 zeros outside of the main diagonal. Now let's perform some products. We're just gonna see, right? So first we have A equals this and B equals that. We're going to multiply A times I3. So that is A, -1, 2, 0, 0, 1, 3 times I3. I3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's an I3. So now let's perform the product. So that equals, but remember, you know, when you multiply by I, it's not gonna change. It's not multiplying by 1. So we expect that not to change the matrix that we have. And we expect the matrix we get will have the same number of rows that A has and the same number of columns of I3, which is also 3. So now let's see. This column multiplies the row, the first row, the second row, and the third row to create the first row of the result, right? So -1 times 1 is -1, and then the rest is 0. For the second row, you're gonna have the -1 times 0, 2 times 1, and 0 times 0. So that's 2. And then the third row, everything will be 0 except for 0, but 0 times 0 is 0 too. So I'm talking about this one times this one is 0. This one times this one. I'm talking about -1 times 0 is 0, plus 2 times the second 0 in the second column, in the second column of the first, the second 0 in the third column, that's 0. And then this 0 times 1 is also 0. So that's 0. Well, obviously it's 0 because that's what it was. And we expect this to be the same as A. And then we continue with the second row of A, of the matrix A. So the second row, we're going to multiply it by row 1, row 2, row 3 of I3. So that's 0 times 1, 0 times 1, plus 1 times 0, plus 3 times 0, that's 0. Let's go ahead with the second row, second column, sorry. So that is 0 times 0, plus 1 times 1, plus 3 times 0, that's 1. And then finally, we're gonna do times the third column, the third row in the second matrix. So that's 0 times 0, plus 1 times 0, plus 3 times 1, that equals 3. So that's the same matrix A that we got. We multiply by I3. We did not expect anything different from the same matrix. It's like when you multiply by 1, you cannot expect, unless your multiplication is not possible. If you multiply by I1, I2, I3, I4, I5, all the I's, when you multiply by it, if the multiplication is possible, then the result will be the same matrix that you had prior. So that's why I'm gonna ask that you perform B and C on your own to see what is it. But you expect them all to end up being the same matrix that you multiply. So the properties of identity, that's the summary of everything that we were saying. If I multiply I in a matrix, it equals to the matrix. Or it doesn't matter if you swap it. Like if you change position, you remember when I was saying that multiplication of matrices is not commutative, but not for I. Like for I, it doesn't matter which side you put it, it's still going to work and it's gonna give you the same answer. So I times A, if the multiplication is possible, that means the number of row, the number of column of the first matrix is the same as the number of row of the second matrix. The multiplication is possible if one of the two matrices is I, the answer will be the other matrix. All right. And then also, if you multiply, so yeah, that's exactly what I'm saying, and that's the version of if it's the same matrix or if it's not different. If it's I, as long as you can perform the multiplication, then it's going to be the second matrix that you multiply by I. An identity matrix has properties similar to those of the real number one. We talked about that, right? If you multiply by one, it's not going to change anything. That's the same thing if you multiply by I, whatever the I, if it's I2, I3, I4, any I, if the multiplication is possible, then it's not going to change the answer. And that's exactly what one does for real numbers. All right. So now let's see the inverse of a matrix, right? The inverse of a matrix. I mean, the one thing that the set of matrices has a lot of similarities as the real numbers, but some of them are different, and that's why you need to be careful. So we know that if you multiply matrix A times its inverse, it's the same as if you multiply its inverse times the matrix, then it gives you I. So that's a good thing, because if you have 1/2, for example, right? If you multiply 1/2 by 2, 1/2 is the inverse of 2. What do you get? That's 1. Or say 2 times 2 exponent -1, which is the inverse of 2, right? Or 1/2. See? What do you expect? You expect 1. And that's exactly what happens for the matrices. If you multiply a matrix by its inverse, then it equals to the I of the set. Like, we're talking about square matrices. Square matrices are matrices that have the same number of columns or rows. They have the same number of rows as number of columns. So if the number of rows is not the same as the number of columns, don't even try to talk about it. And a matrix that the inverse is not existed. So not every square matrix has an inverse. Well, I know if it's not a square matrix, it has no inverse. But now, what they are telling us is that if the matrix even if the matrix is square, that doesn't guarantee that it has an inverse. And when the matrix has no inverse, has an inverse, A exponent 1, but it's like A -1, then A is said to be non-singular. And if it doesn't have an inverse, it's called a singular matrix. Does not have. That's when it's singular. When it has an inverse, it's called a non-singular matrix. Well, we know that when we multiply a matrix with its inverse, it equals to I. So we have 2 square matrices of order 2, dimension 2, which means same column, same number of rows, same number of column, and it goes 2. Now they tell me that this one is these 2 matrices are inverses of each other. What do you expect if you multiply the 2 matrices? Well, you expect the product A times, so I'm gonna say find A times A inverse and B A inverse times A. You expect that to be I. I2, right? But let's do it. So A times A inverse equals, so that's 3, 1, 2, 1 times 1, negative 1, 1, negative 1, and negative 2, 3. So now let's perform. I'm going to go faster for this one. So that's 3 times 1, 3, 3, and 1 times negative 2. So that's 1. 3 times this. So 3 times negative 1 and 1 times 3. So negative 3 plus 3, 0. 2 times 2 times 1, 2 times 1, 2 times negative 2. I mean, 2 times 1. I'm working with second column. 2 times 1 plus 1 times negative 2, that's 0. And last, we're gonna do the second column, the second row and first and second row, second column. So that's 2 times negative 1 plus 1 times 3. That's negative 2 plus 3 equals 1. So that is the, that's the I2, right? Now let's see what A inverse, that's A, B, A inverse times A. Let's see what is it. So that's going to be the second matrix times the first one. So that equals, I'm going to do this one slower. First row that multiplies the first column and then the second column. So that's 1 times 3 minus 1 times 2. That equals 3 minus 2 equals 1. Now we're going to do the second column with the first row and second column. So that's 1 times 1 minus negative 1 minus 1 times 1, that's 0. Now I'm working with the second row of the first column of a first matrix that I'm going to distribute over all the columns. So this one times this one. So let's start with the first column. So negative 2 times 3 plus 3 times 2, that is 0. Now let's work with the second column with the first row, second column. So negative 2 times 1 plus 3 times 1, that equals to 1. Also I2. We expected that because we multiplied a matrix A by its inverse. Now the next thing that we're going to talk about is the steps to find the steps for inversing n by n non-singular matrix. Well, we talked about, all the operations to perform on the rows of a matrix in order to get this matrix to an echelon matrix that was in topic number 2. Now we're going to do the same thing to inverse a matrix if the matrix is a non-singular matrix. Well, basically what we do is we're going to find the echelon matrix, which means find one on the main diagonal and then 0 at the bottom, and work it back to get the zeros on top as well, to get the augmented matrix as the identity, and the other one that was A. The identity, we're gonna get it to a matrix, and then the one that was A, to transform it into I. Well, basically that's what you do. So you see, that's your augmented matrix. You separate it, the A and the I on one side, and then you perform work to get this, the I switched. You work and get the I switched to the other side. And once you get that, and then it creates the A you get is the identity, once you get the identity where you had the A, and you get another matrix on the other side of the augmented matrix, then it creates the inverse. So let's go ahead and try this example. So we're going to find the inverse of A equals. So first, let's write the augmented matrix. So that's A, 1, -1, 0, 1, 3, 4, 0, 4, and 3. And then we're going to add the I3 because it's a 3 by 3 matrix. So that's 1, 0, 0. That is 1. Nah, that's 0. So we already have a 1 here and a 0 here. All we want is to get a 0 right here. What would you do? Let's perform row. We're performing row 2 receives row 2 plus row 1. And that will give me what I want. So we are changing row 2 only. So that's 0, right? And then row 2 plus row 1. So that gives me 4. Another 4. That's 1. Another 1, 0. And then I want to get a 1 here. So I make row 1, row 2 also receive itself divided by 4. So row 2 receives 1/4 of row 2. Again, row 2 is the only thing that's going to change. Otherwise, everything now for this step, I'm not changing them. So row 2 is changing. This one will remain 0. And then everything will be divided by 4. So that's 1, another 1, 1/4, 1/4, and then 0. Okay. And then now I want to get a 0 below the 1 in the second column, right? So what I can do here is I can make, I want a 0 below the second column, 0 below the second column, and then I guess we can make R3 receive, we can make R3 receive itself minus 4 R2. So R3 is the only thing that's changing. R3 will be the only thing to change. So we will have this as R3 is changing, but the zeros are not, obviously. Because I'm doing R3 receive let me erase everything. So R3 receives R3 plus 4. So R3 minus 4 R2. Let me start with these two. So that's 0, 0. So that gives me 0. Now let's go to the second one. This one, R3, 4, 1. So that's a 0. We go with that. R3, 3 minus 4 times R3, 3. 4 times 1. So that's negative 1. And then we need to do the same operations over here. So that's R3 is 0. R3 is 0. We're working with that. Minus 4 times 1/4. So that's negative 1. Also negative 1. And then lastly, we're gonna have, we'll have, that one was 0. That one was 0. Oops, my God. That one was 0. And then this one would be 0 and 1. So that's negative 4. So let's see again. That's 0 minus 4 times 1. That's negative 4. So zero minus, so that's 1 minus, okay, so that's let's do that again. That's 1 minus, yeah, so that's positive 1. And then next, what we can do here, because we already have 0 here, we want 1. We want a 1 at the last corner. Then we can make R3 receives negative itself, right? So that's going to change the whole thing into not so different from what it was, because only R3 will switch sign. Only R3, the signs of R3 will change. And as you can see, there's a lot of math involved in this. If you're not paying attention, then you would be lost. So then that's going to be all the signs of column of row 3 will switch. And then now we are almost where we want to be, right? We are almost where we want to be. The next thing we can do is we can, because we are already at the point where we see the echelon matrix, right? We see the echelon matrix. Now, because we have the echelon matrix, it tells us that we already have one part of this work done. Now, what can we do? We want to eliminate these ones, this one and this one. We want to turn them into 0 to get the identity 3. All right, so how do you eliminate these two ones? You can decide which one you eliminate first, but I want to eliminate the one in R2. So let me make R2 receive R2 minus R3. So R2 receives R2 minus R3. Okay, now that takes me to changing R2 only. That's fine. And then the rest will be the same. So let me copy the whole thing here. And then R2 will be changed into subtracting R3 from R2. So R3 from R2, these are 2 zeros, it's not changing. R2 from R3 is 0, this one is not changing. These ones will be 0 because you subtract 1 and 1. So that's going to be 0. So we're going to do the same thing here. So that's R2 1/4 minus R minus 1, that is negative 4 plus 1, that's negative 3/4 in R2. R2 minus R1, negative 3/4. Same thing here. And then this one will be 0. So that one would turn into 1. Okay, now last thing to do is to get this positive 1 to 0. How do you get that? We would make R1 receives R1, obviously, R1 should always be included, minus, let me say R2, because that's the only thing that's not changing my whole structure. So let copy this, and then we're going to change only R1 because everything else is already perfectly fine. So let me see. The first one is not changing because R2 is 0 below it, so 1 stays 1. This one will be changing into 0. This one will stay 0. And then this one here, we do 1 minus 3/4, so minus positive 3, so that's positive 3/4. So that equals 7/4. And then the second one is 0 plus 3/4. So that's also 3/4. And then the last one is 0 plus 1, that's 1. Zero minus 1, sorry, it's 0 minus 1. It should be minus, so that's minus 1. Because it's R1 minus R2. It's 0 minus R2, so that's minus 1. Now, since we swapped the matrix that we had before with the I, remember how we started this? We started with the I, with the augmented matrix. I3 was here, and then A was here, right? Now we do work all the way down here so that we get I over here, I3, and then we get a matrix here. The matrix you get here is automatically A inverse. But we can always check it, correct? But I know that A inverse here, you can check it by multiplying it by A to see if you get I back. But in a test scenario, you may not have enough time. You may want to make sure your operations are perfect all the way down until you get I. But most of the time, there will be a lot of confusion and lost. So that's A equals, let me copy my stuff here because I would not have enough time here to. So that's my inverse. That's my A inverse. -1 this is. So this is my A inverse. 7/4, 3/4, -1, -3/4, -3/4, 1, 1, 1, -1. Okay. So now in this example, we are trying to see how matrices that have no inverse or singular matrices react when we are performing operations to when you are performing operations, so we know when we don't have inverse. So say for example we were trying to perform operations so we can find the inverse of this. What would you do first? So let's do it. We're trying to get a 1 here, but let's first write the augmented matrix. So that's 4, 6, 2, 3, and add I2 here. 1, 0, 0, 1. I want a 1 right here. So let me do R2, a 1 receives 1/4 of itself. Then automatically I would see that I have that's a 1, and that's the purpose of me doing this operation. And then 1/4 of this would be 2/3. I mean 3/2. 1/4 and 0. Now I need a 0 right here, right? So let me do R2 receives, that's R1. Let me do R2 receives R2 minus 2 R1. And then it gives me that, it will give me that result. R2 is receiving, so R1 will be okay to stay. So, you know, it's R2 minus R2 R1, right? So for the first column, it'll be 2 minus 2 times 1, that's 0. So the second column, it will be 3 minus 2 times 3/2. 2 cancels this, that's 0 also. So once you get 0 all over this, it's a sign that something would be wrong. And also you would try to do this, so that's R2 0 minus 2 times 1/4. So that is negative 1/2. And then you would have R2 1 minus 2 times 0, that is 1. Okay, so the 1 stays. So R2 minus 2 times R1. Okay. Now, looking at this, what you say is the fact that you have zeros all over here, then these lines are linear combination of each other. They are a combination of each other. They are a combination of each other. So that explains why you would not have inverse for this matrix, because the lines are independently linear. They are dependently linear. So it's like line, the columns, not columns, the rows are linear dependently linear. The rows are dependently linear. So it's like you have row 1 is something I don't know, a number times row 2. Whenever you have that, then it's not going to be, there will be no inverse for this matrix. And you get that whenever you have zeros for all of them when you're trying to get 1 to 0. And it gives you both of the terms, or it gives you the entire row 0. Whenever you get the entire row 0, as you're trying to get one of them 0, for any matrix, it's where you say, you make the conclusion that this matrix is a singular matrix. So A is singular. And lastly, we want to solve this. We want to solve this system by using matrix. So you do the same thing that you would do when you're looking for the inverse of a matrix. Now you're going to first make sure that you write this system as echelon matrix, and then you would solve it. So let's go ahead and write the matrix of the system and then the echelon matrix and find the inverse. So first you need to find the matrix form of this system. The matrix form of this system. And then you would find the inverse and multiply both sides of this equation by the inverse. So let's find the matrix form of this system. So first we need to make sure that the x's are aligned and the y's are aligned and the z's are aligned and the numbers are on the other side, and which is clearly done on this case. So let's write the matrix of the system So in general, your system is going to be as A for the matrix of the system times, I will call this one as a x, but it's a variable, it's a x that has components x, y, x1, x, y, z. And then I would call this one a b, which is a vector. It's a column vector, and x also is a column vector of 3 elements. So in this place, I'm going to put the coefficient of x, so that's 1 here. Coefficient of y next to it in the row, and then coefficient of z, in this case 0. Coefficient of x for the second column, second row, negative. Coefficient of x, -1. Coefficient of y, 3. Coefficient of 4 of z, 4. Coefficient of y of x is 0. Coefficient of x of y is 4. Coefficient of z is 3. And then x, y, z. Just take this one just like it is, 3, -3, and 2. Now, when you finish with the system, writing the system in the matrix form, what you want to do is you want to make sure that you write it, you multiply by the inverse of the matrix A on the left side. So basically, if you have that, right, your matrix, your system is AX equals B, right? Now, if you multiply on the left side by A inverse, that will be I. Remember what I said, multiplying by I is not multiplying by 1. So that's going to be X equals, and then you would get a vector, a column vector for Y, for of numbers, because A inverse is a matrix of numbers, and B is a vector, column vector. Then you would give you a column vector for your result. Okay, now we need to find A inverse. Well, you're going to use the same techniques that we use over here to find A inverse. I'm not going to have enough time in my video to do it, but I know that A inverse equals, so that's what you're going to do. That's what you need to do. But before you do that, you need to find A inverse. Use the column, the row operations to find your A inverse, which I'm going to give you. A inverse equals, well, actually, that's the A we calculated. That's exactly the A that we calculated its inverse. That's this. So we found it here, so we can just bring it here for us to work on or work with. That's A inverse. We bring it here and multiply both sides by this. So that's A inverse times the A okay? And then X, XYZ. That equals to the A inverse times the B which is the second side of your equation in vector form. And then now this is I3 times X equals, now we need to find this. I3 times X is X equals, then we need to find this. We perform the multiplication. We need to perform that multiplication. And then we will get X, which is the vector, this vector, is equal to the multiplication here. We perform this the whole multiplication. That is, let me write this as that, okay. Let me bring it here. So that's the first column. We multiply by this. So we would have three times the whole thing. So that's 21 over 4 plus 9 over 4 minus 3. And then we would do the same thing with the second column, the second row. So that's going to be this. Negative 9 over 4. Negative 9 over 4. And then plus 3. And then lastly, the third row will multiply this. So that's 2. I guess I need to. And then that's 2 plus 2 minus 2. And then finally, you get this equals to 1, 2, negative 2. So 1, because you're gonna have, that's 30 over 4 minus 3. Then you do 4 times 3. That's 12. So that's 30 minus, so that's plus. No, that's minus 9. So that's not 30. That's 21 minus 9, that's 12. And 12 divided by 4 is 3. It's 3. 21 minus 9 is 12. 12 divided by 4 is 3. That's a 2. That should be a 2. Let me see again. So let's try to fill in this matrix again by multiplying this A inverse and the B. So we're gonna take this column, first column, times this row, first row times the column, right? So this one times 3, this one, the second one times negative 3, and the third one times negative 2. So we're gonna try to do this. So first column, first row times 3 times each of these. So 7 times 7/4 times 3, that's 21 over 4. 3/4 times negative 3, that's negative 9 over 4. And then negative 1 times 2, that's negative 2. Okay, so that's the first row. Let's work with the same, in a similar fashion with the second row. So first, we multiply the first one by negative 3, the second one by negative 3/4 by positive 3. So that's negative 9/4. Negative 3 fourth times negative 3/4 times negative 3, that's positive 9/4. And then 3 times 2, that's positive 2. 1 times 2, that's positive 2. Okay. And then last, we will multiply 1 times 3, that's 3, plus 1 times negative 3, negative 3, and then negative 1 times 2, negative 2. So now let's perform the operations. To finish with this, we get 21 minus 9 over 4, that's 12 minus 2. 12 over 4 minus 2, 3 minus 2 equals 1. That's this one. Okay, next. That can negative 9 over 4 plus negative plus 9 over 4, that's 0. My plus 2, so that's 2. And last, 3 minus 3 equals minus 2 equals that's 0, so that's negative 2. And then, so if x, y, z equals 1, 2, negative 2, your solution set is 1, 2, negative 2. So that finishes the lesson, the video for lesson number 4, and that's quite one of the most complicated, because it has a lot of operations and the minus, the plus, and all these that you need to manage in this. But I hope that this will not make it so hard for you. And then since it's recorded, then you can watch it multiple times. The mistakes that I make too, hopefully that they can help you pinpoint some of the mistakes that you need to watch.